Hey everyone, it's Dr. Calkins. So today, experiment 21, getting close to the end of our semester. This one's called Breaking Bad, Making White Powder. So we're not making methamphetamines because I don't want to go to jail. But we are making aspirin, which is a white powder nevertheless. We're also going to be making oil of wintergreen. So it's going to have a pretty smell, which unfortunately you won't be able to smell through a YouTube video. A couple definitions as we saw in lecture. So a mole is how we represent grams on the periodic table. But in order to represent a mole, we have to realize that there are trillions upon trillions upon trillions upon trillions of those atoms or compounds or molecules or particles. So stoichiometry is the idea of how to calculate, which is what's going to be practiced in this lab. You're calculating how much. So just like if you have 4 slices of cheese and 10 slices of bread, one's going to run out first, and that's what stoichiometry is about, telling you who's going to run out first in chemistry. Molar mass, again, is the mass on the periodic table. It's relative to that mole. It's also relative to Avogadro's number. So there's a joke about that. If you have a mole problem, call Avogadro. We'll see that coming up in our lab as well. And then lastly, the mole ratio. Really, you only need mole ratios to determine this to that. So products to reactants or ingredient to ingredient, ingredient to product kind of ideas. So we use coefficients. Remember, those are just the balanced chemical equation coefficients, the big numbers in front. You can use subscripts. That's a little bit rare in Intro Chem especially. That's really when you're looking at atoms to the overall molecule. Typical problems, and most of these are done for you. You just have to plug them in. Typical problems are going to give you some kind of mass that we're going to get on the balance in lab. You're going to look for the mass on the periodic table. That's going to be division, so that those grams cancel. Molar mass only works when you assume 1 mole, so again, that's the definition of molar mass. Moles of our reactants and products, those are things we can find from the balanced chemical equation. And then molar mass of the product we can find on the periodic table by adding up all their atoms. Just remember that is per 1 mole, that's the definition. This would calculate theoretically how much we can make. Just like on the exam, you can get theoretically 100 questions correct, which rarely ever happens. What you actually get would be just like a percentage to calculate your grade. It's what you got based on what you could have gotten, times 100, and that gives you a percentage. So piece divided by the whole, we've seen that all semester long. So this is one of my more favorite labs, not only because it's making something that looks like methamphetamine, but it's organic chemistry. And really the only chemistry that I enjoyed in college was organic chemistry. That's where I got my PhD. So this is going to be most similar to what I did for several years in my fume hood as I was getting my degree. I didn't really enjoy a lot of the math, and I got C's in all my calculus classes, but C's can get you PhDs eventually, as was my case. So let's take a break and go to lab. All right, so looking at page 148, we're going to take 2 grams of salicylic acid and weigh it out and put it into a Erlenmeyer flask. So we're going to do that now. All right, so to do this, we're going to take our weighing paper. I like to fold it into kind of diagonals so that it's easier to pour. We're going to put that on the balance. And it's very important here to hit 0. We don't want to weigh the actual weigh paper. And then we take our spatula, or in this case scoopula, and take some out until we get to 2 grams. So we'll come back when that happens. All right, so there we go, 2 grams, and we'll take that across the lab to our flask. All right, so we have our 2 grams. This is our actual mass, so make sure you record that down here. And we're going to add it to our Erlenmeyer flask. This is why I like to fold the paper beforehand. The other ingredients we're going to need are 5 milliliters of acetic anhydride. So that's here. We're going to add it through a graduated cylinder. And then we also need 5 drops of concentrated battery acid, which is called sulfuric acid. This is our catalyst. It's going to speed this reaction up so that we can do it in 10 minutes and not 10 hours. So we'll come back when those have been added together. All right, here's our acetic anhydride. You missed out on some terribly vinegar smelling solutions, but nothing too fancy to see. It's kind of looks like water. But it's going to react with our molecule to make aspirin. And then here we have sulfuric acid, so we're going to take 5 drops. So this reaction goes relatively quickly. So 1, 2, 3, 4, 5. And it's growing. Close enough. Come back in a minute. Alright, so here we have our hot plate turned up to about 250. We added some boilizers, just like the name implies. That helps boiling a little bit easier from the bottom. So it's just little rocks floating around there to help it boil. We're going to put our solution in there and let it boil. As it floats, we're going to aim this towards the back so that if it splatters or bubbles out, it'll go towards the back, and we'll leave that for 5, 10, 20 minutes. Alright, after about 5 minutes of boiling so far, it's just a clear solution. So it's all dissolved in our acetic anhydride and sulfuric acid, so we're going to let it boil for another 5 minutes or so. Alright, we're approaching 10 minutes, and notice down here these little rocks, that's what they do. They kind of bounce around, give some contact so that bubbles can be formed. That just keeps our flask from trying to bounce in and out and splatter water inside of our reaction. So we're going to take this out. Notice still very clear. Got a little bit of color to it, but not much. And then because of that acetic anhydride, it's very reactive with water. That's why we didn't want it to boil into our solution. We're going to add a little bit of water to kill it. So it may or may not make a little bit of noise, but it could. So definitely angry. We killed any leftover acetic anhydride. That's called a quench. And then to cool it off, we're going to add our 40 mils of distilled water to dilute it. Notice it's trying to crystallize already. So we're going to let it cool down for a few minutes. Notice it's slightly water soluble, so it's clearing back out. So we did see our crystals for a minute, but now they're gone. But with ice, we can bring them back, and that's called recrystallization. So we'll come back with our ice bath. So this is the rewarding part. We're going to take this clear solution that looks like water and put it into our ice bath now that it's cooled to room temperature. And then we're going to stir our solution for about 10 minutes until we start to see crystals. So we'll come back when crystals are starting to form. Alright, with a few minutes of stirring, we're already getting to kind of a milky color. So we're starting to get there. We just need to keep going. Alright, so we're a few minutes later. Notice it already is starting to make enough to kind of settle out. See our aspirin starting to form there at the bottom. So we're going to keep going a little bit longer, but we're definitely on the right track. Alright, so after 5-10 minutes, it looks like we have plenty of crystals that have crystallized in our Erlenmeyer flask. And then we're going to come back over here and set up our filtration. So here's our vacuum tube. It goes to the yellow, which is vacuum. Here's our rubber support collar. It's going to go on top. Here's our ceramic Bugner funnel. It's got holes in it, so we're going to have to cover those up with some filter paper. So we have some filter paper here that goes on top. And then we're going to have to go to the ice machine to get our water bottle. Alright, so here's our ice box. We're going to grab our wash bottle of distilled water because aspirin is slightly water soluble but less so in cold water. We're going to seal the paper by adding water to it. It's going to get it nice and wet, and then as we turn the vacuum on underneath the fume hood, notice it sucks through and you can hear the vacuum on. It has plenty of suction. We're going to take our aspirin from before, and then we're going to pour it over top of that filter paper. It's going to suck the water away, and then we're going to rinse with cold water the remaining aspirin from the flask. This will also wash away any sulfuric acid that's left over. So a lot of people that make methamphetamines, they skip this step, and that's why they have bad teeth. But again, this is aspirin. Still has sulfuric acid as a catalyst though. So notice our aspirin is collected on top. We're now going to stir it, and it's going to look like powder. And we're going to continue to do this with air being drawn through it from the vacuum pump until it's nice, dry, and fluffy. And what we are observing is our actual aspirin. So it'll be our actual yield as we take it over to the balance here in a moment. So we'll come back for that. All right, so it's been going for quite a while, and we had air pull through them. Notice now they're nice, dry, and fluffy white dust. So what we're going to do next is turn our vacuum off. It's underneath here. Notice the noise went away. Still has a little bit of suction, so we're going to gently break it free. And then we're going to take this over to the balance. All right, with our new piece of filter paper already pre-folded, we're going to hit 0, so we're not weighing the filter paper. And then we're going to take our crystals over and scrape them on and weigh them. And this is our aspirin. So we're going to come back when this is done. All right, here we have 1.933, 1.934, so record 1.934. All right, so back to our lab book, we have that 1.934 here that goes for our actual yield. Now we need our purity test color to finish this page. So notice here it says add some iron chloride to our aspirin. It will turn yellow, which is the color of the actual solution, kind of an orange. And it'll turn yellow if our phenol functional group has been replaced by our ester that we need in aspirin. However, if it's decomposed or if it never reacted in the first place from salicylic acid, it will turn purple. So purple is bad, yellow is good. So here we go over to the stuff that I just made. And let's give it a drop. And it does have a little tinge of purple, but mostly orange. Given the amount of time that we cooked it, not too bad. So it's got a orange to maybe a slight tinge of purple for our purity test color. So it's pretty good stuff. And to give you an idea, if we were to take real aspirin, and this one has a expiration date of 3/19, so it's pretty old. Let's take out one pill and show you that even with this pill that's been in this bottle, hardly unopened, watch it. Notice it turning very dark purple very quickly. And that's why you shouldn't save medicines. They do decompose over time. All right, we do have a page of busy work to deal with on page 149. So we're gonna do that here in a few minutes with our other reaction. We're going to go ahead and turn the page over to methyl salicylate on page 150 and complete that experiment, and then we'll do all the busy work in one shot. All right, so in the synthesis of methyl salicylate, we need to use a test tube. So because we're not going to scrape anything out of it, we're going to weigh it before and then after. So we're going to weigh it now. Already hit 0. And record this number at the top of page 150. 30.124 is good enough. All right, so we have our salicylic acid. We have our test tube supported by an Erlenmeyer flask so it doesn't tip over. We already have our folded weigh paper. We're going to put it on there. Again, hit 0, so they're not weighing the wax paper itself. And then now for this experiment, we only need 1 gram of salicylic acid. So we're going to start adding that and then come back when we're finished. All right, here we have our 1 gram of powder. And we're going to take that and then put it in our test tube. And then we'll be right back. All right, next we need to add 10 mils of methanol or methyl alcohol. We have that here. And then our catalyst, again, sulfuric acid, battery acid, only 3 drops. So we're gonna get that ready and then be right back. All right, so we're gonna take our 10 mils of methanol, kind of wash down the sides of our test tube. And then we're gonna take our 3 drops of our battery acid and put that in too. and want to grow on. So let's take this over now to our hot plate, and tube only goes inside to boil. We're going to let this boil until it's complete, but even now, because methanol is so low in boiling point, notice it's already boiling, so that'll be quick and we'll come back. Alright, we've cooked it for over 10 minutes, seems like, and notice now we have a little bit of sludge left, but notice as it sits out, it's starting to make crystals up here in the top, and because our hot plate was so hot, it really just melted our crystals down there because we were impatient. So as they start to form a solid, we're going to wait again and subtract the original test tube weight to get the actual yield for methyl salicylate. So we'll come back for that. Alright, so here we are at the balance. We need to take our container, put this on, and hit 0. And then we're going to come in on the top and bring in our test tube. And then we're going to come back for a weight. Alright, to match the lab book, we went ahead and cheated. 31.078 is our final weight for our test tube. Subtract those two values at the bottom, and the difference will be your actual yield of methyl salicylate. Alright, so to get our actual yield one more time, we need to take our final mass, which was 31.078, subtract our initial mass from up top, that was 30.124. That subtraction will go here, so I'll give you a minute to do that now. To finish this lab, we need the odor, which is difficult for YouTube, but in order to do this, again, you would wave it towards your nose. And you can learn a lot about a student in this situation, because some will say it smells like Skoal, others will say it smells like Icy Hot, and then some will say it smells like Lifesavers, all of which have oil of wintergreen hiding inside. All that is left is busy work on these 2 pages, so we're going to go back to the document camera and finish this lab. Alright, we're back, and I'll give you a minute to find page 148. We're going to do the busy work of both experiments that we completed. Our mass of salicylic acid was about a perfect 2 grams. We recorded that earlier from the balance. And then after we filtered, we weighed out another 1.934 grams of actual aspirin. Now we have to go to the next page and figure out how much could we have made. Starting at the top, we have our balanced chemical equation. This is 1 to 1 to 1 to 1. That's going to help us with our mole ratio, so think about those in this position. We have salicylic acid, which is the molecule that we made. Notice here's our phenol, here's our arene, and here's our carboxylic acid. Acetic anhydride is basically like an ester on both sides. It's a hybrid group that we don't really cover in Intro Chem. But notice the major change is our phenol became an ester. This will help you in one of your questions later. So we had a phenol and salicylic acid, and aspirin has now an ester. So what's unique about that is the acid's still there. So aspirin's still harmful to your stomach because that acid's very acidic. Our byproduct was acetic acid, so we would have smelled vinegar during this entire reaction, and I definitely did. So as we get to our calculation down below, we need the mass of salicylic acid. So we're going to put that out front. That's our 2 grams of salicylic acid SA. Then we're going to set up 3 conversion factors, just like above. Remember, in these kinds of problems, it's always moles on top and bottom, and on bottom. It's like your mole runs across the surface of the ground, and then he gets scared because this is math and he dives underneath. That's always the case. And what's important now is this is always 1 mole. This is always 1 mole when we're dealing with molar mass. This is grams of salicylic acid because they need to cancel. This is salicylic acid. That's the definition of molar mass for 1 mole. In order for these to cancel, they have to come over here, salicylic acid. We have moles of aspirin, so this is grams of aspirin. I'm just going to say ASP for short. That's going to be respective to 1 mole of aspirin, which needs to cancel up top. So notice that diagonal cancellation all the way through. That's something we've seen for now 2 chapters in a row. Both the metric chapter and the mole chapter have that in common. Remember our equation for salicylic acid, which was our first one? We need our 1, so that goes here. And for aspirin, it's our second to last molecule, so that's this one. That goes there. Next, we need the mass. I give those to you. Plug that in here for salicylic acid, so that'll come around here. And the aspirin mass will come up top. Remember, in your calculator, you're going to be dividing down and multiplying across the top. So times it by 1, divide it by 138.12, times it by 1, divide it by 1. Multiply it by 180.16, and then divide by 1. And get your answer. This is the theoretical yield of aspirin based on salicylic acid. But we had another ingredient, and that was acetic anhydride. We need to make sure one of these 2 ran out first. We need to figure out which one. So that's called limiting reagent. So in this situation, we had our other number that was already given to you. This one was the 5.40 grams I gave you already. That goes out front here. And as we do that, we're going to set up the same kind of conversion. But this time I'm going to let you do it. Just remember, moles are always on top and bottom, and on bottom. This is acetic anhydride, AA. So make sure that as you fill this in, you cancel it across. I'll give you a chance to do that now. And as you do this, the lesser of these 2 answers, because both are theoretical yields, the lesser of the 2, so whichever one is lesser, that is the limiting reagent. So we're going to go back up top and circle that one. I'll give you that to do now. Alright, so I went ahead and calculated the answers. Again, you need to fill that in for the upload. We had a 2.609, so basically 2 grams of salicylic acid can make 2.609 grams of aspirin. And from our acetic anhydride, which was the excess reagent, we could have made up to 9.53 grams of aspirin. So we can only make the lesser amount because we're going to run out of salicylic anhydride. So we go up to the top and circle it. This is our limiting reagent. That's the one that ran out first. So the one that runs out first is our theoretical yield of aspirin. So that's our 2.609 grams of aspirin. We want to put our mass of aspirin that we found in class, which from the previous page was 1.934 grams of aspirin that we weighed on the balance, times that by 100, and you'll get the answer here. We already know the answer from above. 2.609 was the maximum possible. So I'll give you a minute to finish that now. All right, time to rinse and repeat. We have our mass, the mass that I gave you. We're going to take those to the next page. Eventually we'll need this one at the very bottom of the next page when we do that percentage one more time. So in this reaction, very similar. For our oil of wintergreen, methyl salicylate, we take the same molecule, salicylic acid, which is the cool part, because if we change this group to an ester, we make aspirin, but if we change this group to an ester, we make oil of wintergreen, which has a very unique smell. In order for this to happen, we reacted with an alcohol instead of an anhydride. Still use the same catalyst, still cook it for about the same amount of time, but now we got a flavor or a smell instead of a medicine. The reaction here is also 1 to 1 to 1 to 1. It takes one of these and one of these to make one of these and a byproduct of water. So same idea as before, we're going to take the mass from the previous page, which was exactly 1.00 grams of salicylic acid from the balance. Now those 3 conversions, again the setup is right above it to help you along the way. Your little mole gets a little sunshine by running across the top, but then it gets scared, so it goes underneath. That's always the same setup. Just make sure you're able to cancel across each time. We want grams of methyl salicylate here So again, this is 1 mole salicylic acid, so take its mass from above, bring it down here. Grams of salicylic acid, moles need to cancel, so this needs to be salicylic acid to cancel, and it's the first one, it's a 1. And now we're trying to make methyl salicylate, so that's the product. That's the second to last one, so that's this one. They're not always 1s, but in this lab they are. So this is 1 mole based on the definition of molar mass. Go to the periodic table, I did that for you. Take your mass of methyl salicylate and put that up top. That's grams of methyl salicylate. And now you're ready for your calculator. So hopefully you got about 1.102 grams. So now we need to do that again for our other reagent. So flip the page over, steal this number. 7.92 grams of our methanol for 10 mils based on its density. So we take our 7.92 grams of methanol, same little conversion setup as before, moles on top, top and bottom, and on bottom. Just make sure you cancel. Remember, you can take methanol, plug its mass in here, so there. And then same thing over here, methyl salicylate up top is still up top over here. So again, there, goes there. This is 1 mole, just happens to be a methanol. Methanol. And again, this is methyl salicylate, methyl salicylate, methyl salicylate, grams of methyl salicylate, grams of methanol. So notice that perfect cancellation across. Look at our balanced chemical equation. Methyl salicylate was a 1. So was methanol was a 1. So we're going to use this one this time. And we're still going to use that 1. So in the end, it didn't matter. It was 1 or more. So I'll give you a few minutes to calculate that one now. All right, so you should have gotten 37.6 after you fill in those blanks. Again, that was 1 mole there. So lesser of the two is our limiting reactant, or in this case, our theoretical yield. So we had enough methanol to make almost 40 grams of our wintergreen, but our salicylic acid could only make about 1.1 grams. So this is definitely our theoretical yield. So that comes down here. So 1.102, 1.102 grams. That also tells us that salicylic acid again ran out first. It's our limiting reactant. So to wrap up this page, we're going to take our lesser value, which was the 1.102 grams that were possible for methyl salicylate. We're going to take our actual yield, which was the difference in our test tubes. That was that 0.954 number of methyl salicylate that we made, times it by 100, and get your percentage. I'll give you that time now. All right, as we wrap up questions, we're going to deal with the 4 questions on page 152. This one says, how many molecules of aspirin are in 3 grams of aspirin? So notice this is your number, and these are your conversions. So always put your number out front, 3.00 grams of aspirin. And then I'll give you a hint, but I'm not going to do it for you. There's 2 conversions. You have to cancel grams, and eventually you have to get to molecules of aspirin. So here it tells you how many molecules are in 1 mole. Here it tells you how many grams are in 1 mole. So orient those that they cancel, and then that one's done. Very similar number 2. Number 2 is going to have the same idea. You have now 1 gram, so put that out front, of methyl salicylate, or oil of wintergreen. We have 2 conversions, so 2 setups. Same idea, make sure they cancel, make sure they cancel. And what we're looking for again is molecules of methyl salicylate. Lastly, what kind of functional groups are present in the products? So again, this one was based on our reactions from earlier. So we had acids, we had phenols, we had esters. Who switched with who? So write their names and formulas there. what was producing our smell and what was producing our aspirin in particular. We had acids and phenols changing to esters, kind of gives it away. And lastly, why would it be possible to have greater than 100% yield? We were rinsing our crystals with water and then we were drying them. So if we had weighed more than what was possible, what could have been left behind and not possibly dried away to give us more yield than we'd ever expect possible? And that wraps up this lab.